Hello, everyone. You should be able to hear my voice. This is our February 7th lecture. I was in DC, and of course, we are covering some of the origins of quantum mechanics and getting into the Schrodinger equation. When we left off last class, we were talking about unacceptable wave functions, and I need to make sure that I clarify, made a couple of mistakes there. But in celebration of Black History Month, I wanted to cover very famous American Benjamin Banneker. And Benjamin Banneker was a free African-American almanac author, surveyor, landowner, and farmer who grew up in around the DC area in Maryland, and had a really good knowledge of mathematics. So he was born in Baltimore County, Maryland, to a free African-American woman and former slave. Banneker had little or no formal education and was largely self-taught through the use of books. He became known for assisting Major Andrew Ellicott in a survey that established the original borders of the District of Columbia, where I just was, the federal capital district of the United States. Banneker's knowledge of astronomy helped him author a commercially successful series of almanacs. He corresponded with Thomas Jefferson on the topics of slavery and racial equity, Jefferson having earlier drafted the United States Declaration of Independence. Abolitionists, those who wanted to get rid of slavery, and advocates of racial equality promoted and praised Banneker's works. Rittenhouse was an astronomer, responded to Pemberton about Banneker's almanac, his ephemeris, and said that it was an extraordinary performance considering the color of the author, and that he had no doubt that the calculations are sufficiently accurate for the purposes of a common almanac. And he went on to say, every instance of genius among the Negroes is worthy of attention because their suppressors seem to lay great stress on their supposed inferior mental abilities. This guy was an abolitionist. And Banneker did not like that way of thinking. He said a biographer wrote that Banneker replied to Rittenhouse's endorsement by stating, I am annoyed to find that the subject of my race is so much stressed. The work is either correct or it is not correct. In this case, I believe it to be perfect. And we celebrate Benjamin Banneker this morning. All right. So we left off with wave functions, and I misspoke on several of the graphics here. In panel A, this is an unacceptable wave function because it's infinite over a finite region, and it needs to be finite to be well behaved. So we need a finite wave function. We also talked about B, which was multi-valued as a function of x, and we need a single valued function. For C, on the other hand, this is not acceptable because the slope of the function is discontinuous, hopping from one location to the next. We need a continuous wave function. And for D, this is unacceptable because the slope is discontinuous. It's going into some sort of transition and an asymptote and then continuing on. So this is a discontinuous slope. Okay, and moving forward now, we've wish to introduce our Schrodinger equation and the idea that it is our major function to express the behavior of our electrons. And we also want to understand what an operator does. And so we've got, and we introduced, H psi equals E psi, our operator, our wave function, returning of the energy in our wave function. And what an operator does, and we can see this with the Hamiltonian, is it does mathematical work on the wave function and provides information. And in this particular case, this Hamiltonian, h hat is negative h bar squared over 2 times of the mass, and the second derivative with respect to x, plus the potential. And this is known as our Hamiltonian Hamiltonian operator. And what this really does is the Hamiltonian operator provides the complete energy. The complete energy of the system is provided. And like, what does that mean? Well, energy equals our kinetic energy plus potential energy. And so when we look at it, this section, our second derivative with respect to space for our wave function, is our kinetic energy. So it's all right there for us. In much the same way that we would have in classical mechanics, our potential can change, and therefore we'll get into different scenarios in which the potential changes, and therefore the energy of the system will change as well. But when we do the particle in the box model, V of x goes to 0, and then the energy of the system is equal to the kinetic energy of a free electron for a particle in a box. And we'll get into that in chapter 8. But we'll continue with this. And when we look at a wave function in figure 7c.2, we'll notice that it has some curvature, and we're going to highlight the fact that this rate of curvature, the derivative and the second derivative, provides kinetic energy, and we're going to get into that right now, along with the ideas of an eigenvalue function. And so what is an eigenvalue? An eigenfunction is a function psi that does not change after the operator has done work on it. So you can do mathematical work, and then it should return the exact same wave function. This is an eigenfunction, and the energy that it returns is the eigenvalue. And so, again, h psi equals e psi. We have our operator that does work. Psi is an eigenfunction. After the work has been done, it returns an eigenvalue, the kinetic energy, as we saw from the last slide, and then it returns the same eigenfunction. And so these are like fundamental aspects of what is going on with our quantum mechanical functions. It's not debatable. These are the rules in which quantum mechanics operates. And so what we want to do is kind of take a look at a eigenfunction and understand how it should work. And so we're going to do an example. And what we're going to start off with is by looking at a momentum operator operating on a function, should return the energy and return the same wave function. This particular p hat, this is our momentum operator. Of course, we know from classical physics that momentum should be mass times velocity, similar to what we used for our for our de Broglie equation of h over rho. And so we're going to use some of this information and making sure that we stay consistent with the expectations of what we should get when using these equations. So let's go ahead and set it up. First, we need the operator. It's going to do some math, and we also need to have our wave function. So let's get to it. We don't have that much time. So our momentum operator is negative I h bar d over dx. First derivative with respect to x. No big deal. Our wave function is e to the I kx. And of course, you'll recall that I is the square root of -1, and h bar, our reduced Planck's constant, is equal to h divided by 2 pi. Okay, so let's set this thing up. How is this going to look? We've got these two pieces of information. We're going to apply the momentum operator to our wave function. Let's do it. So our momentum operator is operating on psi x, and this gives us negative I h bar d over dx e to the I kx. Now what we're going to do in order to make this a little bit easier with our derivative with respect to x for e to the I kx is we're going to substitute in alpha is equal ik. So then that gets us negative I h bar d over dx e to the alpha x. We take our derivative, we do our der, and what we're going to do is bring down alpha. You'll recall that when you take a derivative with a natural base, then the constant just comes down. So we get alpha negative I h bar e to the alpha x. We'll go ahead and then re-substitute in that alpha equals, what does alpha equal? Ik. Okay, so now here's alpha. So it's I k negative I h bar e to the I kx. And let's simplify this a little bit. So what do we have? Well, we've got two i's, so it's I squared. We've got our negative sign. We've got k and h bar e to the I kx. Okay, so let's look at I. Well, we know that I is equal to the it's negative 1 taken to the square root. If we go ahead and square it, well, I squared is just negative 1. So we've got our negative sign, negative 1k times h bar e to the I kx. So after applying the momentum operator on our wave function, this guy just simplifies to k h bar e to the I kx. This is special because it provides both the energy and our wave function back, our eigen functions. So k h bar is momentum, and an eigen value e to the I kx is a eigenfunction, and we're off and running. And so everything is legitimate. And if we wanted to put it into its final form, we could put in our momentum operator times psi of x is equal to h bar k e to the I kx. Our function, and then our eigen value constant. And this is very similar to the example that we have of 7c.2 in the book. And we're ready to go at that stage. So we kind of can see how we can do some simple calculus and derive out some of these values that we have in quantum mechanics, like the momentum. Let's kind of shift gears a little bit and make sure that we can connect things that we saw previously in classical physics and make that connection to quantum mechanics. I am not doing iClicker since we're online, but just to tease the imagination, true or false, the operator in the Schrodinger equation performs mathematical work on a wave function that results in information about momentum, kinetic energy, and position. True, false, or something else in between, and you can pause and think about this one. And we've got Erwin Schrodinger over there on the right enjoying a glass of wine and his pipe. iClicker question number 2. The probability density of a wave function is calculated by doing what? By adding the wave functions together, psi plus psi, by integrating the wave functions, by taking the complex conjugate of the wave functions and multiplying them together and integrating, or by taking the complex conjugate of the wave function. You can come back to this guy, the probability density question. You can review your notes as well as this video, but you should be able to select one correct answer. All right, so let's get in to connecting our values for our classical operators and making sure that we are doing a good job in receiving the same information that we would have if we use classical physics versus our quantum mechanical operators. So our task is to construct an operator for kinetic energy. The route that we're going to take is to take the second derivative of the momentum operator, the exact same one that we had just used. So P hat is equal to negative I h bar d over dx. So the idea is that you do that derivative twice. And so in this particular case, let's make sure that we define our classical physics. So for our kinetic energy, that should be the same as the momentum with respect to location squared divided by 2m. And if we went ahead and we put the units into place, well, that would be meters squared v squared over 2 times the mass. You'll notice that we cancel off some of our mass units and we're left with 1/2 mv squared. So everything checks out when we consider, it's like, if we were using classical physics, it's the square of momentum divided by 2 times the mass that gets us our kinetic energy. Sanity check complete. In words, square of the momentum divided by 2 times the mass equals our kinetic energy. And so what we're going to do here is take this idea and substitute in our momentum operator. And you'll recall that our momentum operator with respect to position is negative I h bar d over dx. And this is 7c.3 in the book. And so let's go ahead and do this. So our energy, our kinetic energy, should be equal to 1 over 2m negative I h bar d over dx negative I h bar d over dx. This should be our setup. 1 over 2m, similar to what we have here, and then twice our momentum operator. But we're going to be doing it in a similar fashion to what we had before. If we were to simplify this, then the energy operator, the kinetic energy operator, and let's make sure we know that this is the kinetic energy operator, is then equal to 1 over 2m plus I squared h bar squared d squared over our derivative with respect to x. And we can see that this is the second derivative with respect to x. And our I, again, I is the negative square root of 1. And of course, I squared is the same as negative 1. And that's why I put that positive sign there, just to make sure that we reinforce all of our signage, not getting lost. And so our kinetic energy operator is then simplified to negative, because we squared I, so we had a negative 1, so it's negative h bar squared divided by 2m second derivative with respect to x. This is 7c.5. You'll notice that this is the exact same portion of the Hamiltonian operator that provides kinetic energy. Our kinetic energy operator. One portion of the Hamiltonian. If we wish to describe the Hamiltonian, of course, then it's negative h bar squared 2m second derivative with respect to x plus v of x. We should feel very confident. This is 7c.6 in the book. And the question that we have to ask ourselves is, how can we interpret this result? How can we use it? We should be able to get our kinetic energy out of the system. Well, let's think about it with respect to this wave function. This Gaussian curve that's describing the wave function, whatever it happens to be. We need to think of it in a graphic way. It can't just be all mathematics. Let's go ahead and put this on paper and kind of get a pictorial representation. We'll go back to figure 7c.2. Now, the second derivative with respect to x, if it was a car moving, it would be acceleration. In the respect of a function, it's curvature, right? Is it curving up? Is it curving down? First derivative is velocity, the slope. The second derivative is how it's inflecting, how it's actually curving within a region. So let's just write that down. The second derivative with respect to x describes the curvature. Is it a weak curvature or is it strong curvature? Of a function. And the take-home message, asterisk, asterisk, is the greater the curvature, second derivative with respect to x, the greater the kinetic energy. And so we have greater curvature here. This means that this is a high kinetic energy region. This area over here with a more mellow curvature is therefore the lower kinetic energy portion of our wave function. Of course, if we are looking at waves, we can always look back at what happened with the ocean. We've got this massive amount of energy moving over a reef. We've got Kelly Slater there blasting through a barrel at back door. The greater the curvature, the more hollow that wave, the more energy that wave. And as you can imagine, if Kelly Slater had done a poor job of handling that wave, he would have been in very, very fortunate directly on the head. High amount of curvature, second derivative of the wave function equals more kinetic energy. As with waves in the ocean, so with quantum mechanical waves that we're looking at. And let's go ahead and take another version of this information. So this curvature tells us a good amount of information. So observing a wave function and its curvature provides information about the kinetic energy of the electron. Remember, the wave function describes the properties of our electron. Where is it? Its position, its momentum, its kinetic energy. 7c.2, that should be firmly embedded in your DNA by this point. We can also look at 7c.1, where we're looking at a Gaussian function with a certain width. And we'll notice that a very tight function that's given to us in red is our large kinetic energy wave function. Again, the more curvature it has, the larger its kinetic energy, as opposed to this broader wave function has smaller kinetic energy. And we'll get a feel for this again and again, but this should give us a good feel for when we think about drawing waves and thinking about that curvature and frequency. Remember, if something has a high frequency and a short wavelength, then that means its curvature is getting tighter and tighter and tighter. So take this back to the idea of that electron moving inside of an electron microscope, and that lambda was equal to h over rho, our momentum. The greater the momentum, the shorter the wave function of the wave, or the wavelength, and the greater the curvature of the wave itself. And what does that look like? Well, it's going to look something like this. And let's look at figure 7c.3. And it kind of goes through wave functions with an ever decreasing wavelength and increasing frequency. And you'll notice as we go from left to right, the wavelength is decreasing, the curvature is increasing. And what you end up seeing in energy is the idea that you go from having a low kinetic energy area in this section, and it's converting into greater and greater kinetic energy as we move from left to right. Does that make sense? A more gradual curvature of our wave function is indicating our low kinetic energy, and you're converting your potential energy into kinetic energy. And in this case, of course, the total energy is consistent. So E is still equaling our kinetic energy plus potential, and nothing has changed. So let's make sure that we keep that in the back of our heads, especially as we also connect it with the de Broglie wave model and this idea of having a pictorial representation. Now, we've got the feeling like, okay, operators, they're doing work on wave functions. They can provide some fundamental information, momentum, as well as kinetic energy. Let's get into some more properties of these quantum mechanical operators. We'll do that on the slide after our quick quiz. So question number 3, in order to be a well-behaved wave function in Hawaii, a wave function must have which properties? Ability to relax, chill, and chillax, be continuous, be single-valued, be finite, and have a continuous slope, be continuous and be single-valued, or just be wavy. Okay, so let's go ahead and dive in a little bit deeper into these operators and Hermitian and Hamiltonian operators. And we have the cast of Hamilton over there on the right-hand side. And we're going to state this, that quantum mechanical operators that produce observables, location, and momentum are Hermitian and follow that the order of integration and derivation does not matter. Mathematically, it would look like this. Our integration of psi star I, our operator u hat psi sub j d tau is equal to our integration of psi sub j, our operator u hat psi of I d tau. And you'll notice that what we switched here was the position of the wave functions and the complex conjugate. In this particular case, omega hat is just simply the first derivative with respect to space. So how is it changing with respect to space? Similar to our velocity. And we would say again that the order in which you do this integration and derivation does not have any major effect. This is our Hermitian properties. Now, Hermitians are important for a number of different reasons. And I've got this up on the board right here, and we'll just read off. So, Hermitians are important because the eigenvalues, you remember our h bar k equals the energy, are real. So, for instance, our angular momentum, whether or not it's omega star, will also equal omega between our real and imaginary component. Number 2, the eigenfunctions of Hermitian operators are orthogonal. Orthogonal. So that's a new term that we need to dive into. And orthogonality, the functions that make it up, they're going to be equal to 0. And so on the next slide, we're going to talk about orthogonality. And so let's define it now in slide 34. So orthogonality, defined, is the integral of the product of the complex conjugate of the wave functions is equal to 0. What does that mean? Well, we've got two wave functions. We know we need to have this complex conjugate. And so the integral of psi I star psi j d tau is equal to 0. So it's basically saying that when you take the two wave functions, that they're almost like equal and opposite of one another. Because you just integrated across both of them, you took the product of it, and you ended up with 0. And this is true for when I does not equal j, when the wave functions are unique. And let's make sure that, again, we reinforce the fact that psi star I times psi sub j is a complex conjugate. And we'll give a pictorial representation of complex conjugates because it's probably been a little while since you've gotten into real and imaginary numbers again. So let's spend a little bit of time with that. But again, defined, a complex conjugate of a complex number is the number with an equal real part and imaginary part, equal in magnitude but opposite in sign. One is -1, the other is 1. And they cancel each other out. How can we think about this? Quick example would be A and B are real. And you've got two different descriptions. You've got A plus BI and A minus BI. A plus BI and A minus BI, these functions is a complex conjugate. One is adding the BI, the other one is subtracting the BI function. Now let's look at this pictorially, much easier. So let's go ahead. When we look at an orthogonal set of wave functions, it's going to look something like this. And this is projected into Z. So you've got Z equals X plus IY, and then you've got your other part of Z, which is X minus IY. These guys together are a complex conjugate with both an imaginary and real component. And remember, when we say imaginary, it means we are using I. I is being used. And again, the integral of the product of the complex conjugate of the wave functions is 0. Well, what does that mean pictorially? Well, we'd go ahead. We'd integrate under this area. We'd integrate under this area. And since this one equals +1 and this one equals -1, you integrate it together, and together it equals 0. It's so much easier to think about this graphically than anything else. That's the way that I've really absorbed this information well. But you'll recall that in quantum mechanics, we don't want to use Cartesian coordinates. We wish to use polar coordinates. So in the polar form, and of course this is for ease of the mathematics, we would use r e to the I theta, because remember we're not using x, y, and z, and we'd use r e to the negative I theta. Theta being that projection, and we've got 3 different variables in polar form. We've got r, theta, and phi. These two are a complex conjugate again. But it's a complex conjugate in a polar form. And we can think about this, and we'll get into Euler's formula, is that this is justified by Euler's formula, which helps us with oscillatory functions. So the product of a complex number and its conjugate is a real number. The product of a complex number and its conjugate is a real number, a real value, something that you can measure, something that's measurable. Okay, so let's go ahead and take this information and get into what is known as expectation values, like what you should expect statistically if you were to continue to look for a wave function and you integrate across space and say, where am I going to find the wave function and what is its properties going to be, like momentum as an example. And so here in slide 37, in the upper right, we've got Grumpy Cat, RIP Grumpy Cat, he's no longer with us. But for Schrodinger, he had a couple of interesting ideas, and they were summarized with Schrodinger's cat. And I'll let you Google Schrodinger's cat. I'm not going to explain it myself. That's much funner to Google that. But we need to talk about superpositions, where you've got equal probabilities of different states. Schrodinger's cat was a story that Schrodinger made up to describe having equal probability of things being in two states, being up and down simultaneously and not knowing what it was until you made the measurement. And then our expectation values. So let's use a cosine wave function to help describe this kind of idea about expectation values. So we have a psi, we have a wave function as a function of position that's equal to 2a cosine kx. And we use the rho hat momentum operator. And what we would achieve is rho x psi of x is equal to negative I h bar, first derivative of our wave function with respect to x, and this is equal to negative I h bar 2a d cosine of kx over dx. And so you're taking the derivative of cosine kx, and after you do this work and complete it, you end up with a negative sign, another negative, I h bar 2k a sine of kx. Let's simplify this. Well, the negative times the negative cancels out, of course. And we've got this 2. So let's go ahead and simplify this. I'm going to put a plus sign out here just to verify that we know what happened with those negative signs. And we've got 2i h bar k times our returned wave function, which is a sine k of x. Well, this guy, if we're going along from earlier on in the lecture, we've got our eigenvalue. But then, this is interesting. This is no longer the same function. It should return our a cosine kx, and it didn't. So we've got a problem. We've got a problem, unless we think about it in a different way. We can take this result and we decipher it that the cosine function is a linear combination of e to the I kx and e to the negative I kx, the complex conjugate. And so this is going to provide information that the wave functions have this oscillatory behavior and is still a legitimate form. So even though we took an operator, we did work, and we received back a sine function, it's actually not a bad thing. It's actually reinforcing that we've got an oscillatory behavior to our wave function. So we would say e to the I kx and e to the negative I kx do produce momentum as we saw in our previous example, and the way that we can visualize it is that we've got a psi that goes from left to right and has a plus kh bar movement, but then we also have another portion of our wave function which is moving in the opposite direction and has negative kh bar momentum. And of course, this is described as a linear momentum moving along x. If we were to draw it as a sinusoidal function, well, this portion, as it's moving from left to right, is psi plus. And if it was moving back and reverberating like a guitar string in the opposite direction, well, that's psi negative. Both are probable. Both of those can happen equally. That's superposition. So superposition is our wave functions has an equal probability of the wave function moving to the right and to the left, and we could just describe that as psi plus is equal to plus kh bar and psi minus is equal to negative kh bar, like we did previously. In a nutshell, the wave function can be in multiple states at the same time. But then you have to make an observation. Once you've made the observation, then it has to collapse into a state and we can get out an observable. And we should see that next. So we summarize the observation by expectation values. And this is a large number of observations of our wave function after we've gone ahead and used our operator. In this particular case, it was our operator for d over dx. We called it ohm hat, and we'll go from there. So let's go ahead and set this up. And this is described by 7c.11 in the book. So our expectation value, remember we use this as a mean, is the integral of psi star, our d over dx hat, psi over d tau, and again, our omega hat is just d over dx. And this is seen in justification 7c.4 in the book. And what we can say is that this expectation value, once you've taken your complex conjugate, you've done work on it, and integrated it. And remember that when we look at this section of our wave function, omega hat psi, this can also be described by this angular momentum of psi. And we can say that that's psi star omega psi d tau. And omega can come out front. We do our integration of our complex conjugate. The complex conjugate of d tau is normalized and is equal to 1. And this gives us our constant omega, our constant for the system. And we can imagine that that's giving us some amount of probabilistic value. Like, this is the average velocity. This is the average position. In words, when observed, the wave function will have an average value of omega because our constant for the system is the eigenvalue of this wave function. So remember, we're using all of this language, we're using all these terminology. We have to really make sure that we're well versed in all of this language. This is pretty much the end of chapter 7. I'll do a little, we're almost done. I'll do Heisenberg uncertainty principle at the beginning of next class, but we're throwing a lot of information. We've got operators, wave functions, we've got eigenfunctions and eigenvalues. We've also got the idea that we can connect it to classical operators. We have orthogonality. We've got our idea for expectation values and superpositions. So we're being flooded with information, but the best thing that we can do is use our graphic representation, some of our math skills, and also analogy to build up our skill set. I hope everybody has had a great time seeing this video, and I'll see you tomorrow in class. And I should be able to stop our recording right now.